Let's start the session. So, hello everyone, welcome. I'm Sambhav, your senior math instructor. Today we are going to talk about numbers. Not only numbers, but real numbers. The first chapter in your class. So, I will wait for 2-3 minutes so that everyone can join. Then we are going to start the session. In the meantime, if you are having any doubt, any question related to this chapter, real numbers, you can ask us in the chat box, or if you are watching after the live session, then you can ask us in the comment section also. So please put your doubts there. We are gonna resolve them and just wait for 2-3 minutes so that everyone can join. Then we are gonna start the session. This chapter is related to numbers, correct? And we are surrounded by numbers. We have been working with numbers from a very long time. So why we are studying numbers even now? That is one thing that may be there in your mind, correct? So basically we are going to talk about a different set of numbers. You are aware of them, but we are going to talk about them, we are going to prove them, such as irrational numbers. So you are aware of them, but in this session I'm going to prove how to prove the irrationality of any number. So just wait. Okay. So you guys are joining. So I'm just waiting for 2-3 minutes. Then we are gonna start the session. So in the meantime, you can tell me from where you are, what is your real name and everything. Then we are gonna start then soon. Okay. I guess we should start the session, right? Okay. As I told you that we are gonna talk about numbers today, and the name of the chapter is real numbers. So what are we talking about? Are numbers fake also or unreal also? There are no fake numbers or unreal numbers, but there are one more set that is known as imaginary number that you need not to be worried about. In this class, you are going to focus on real numbers only. Okay. Now, in this session, we are going to talk about these topics. First, the introduction part, what is there in this chapter, what to expect. Then, fundamental theorem of arithmetic, the most important part of this chapter. From this concept, you can expect one problem in your board exams. Then irrational numbers. So why numbers are irrational, or what are irrational numbers? So everything we are going to talk about in this topic. Also, we are going to see proof of some numbers, how to prove that irrationality of any number. That also we are going to see in this session. Then we are going to summarize this. This is very easy chapter, very scoring. You can easily score in this chapter. So now let's start the chapter. So introduction. Till now we are familiar with different type of numbers, such as natural numbers that come naturally to us, or also known as counting numbers such as 1, 2, 3, 4, 5 and so on till infinity. Correct? Then we are just adding 0 to that set of number to make it whole. That's why this set is known as whole numbers. So whole numbers are basically 0, 1, 2, 3, 4 and so on till infinity. Then we are gonna do one thing. Till now we are only talking about the positive numbers, correct? Natural numbers and whole numbers. We are gonna add the negative counterparts of the whole numbers or positive numbers. Then this new set will become what? Integers, where we can see all the positive numbers, all the negative counterparts of all the positive numbers, and also 0. 0 is neither positive nor negative. Then then now understand it in this way. Here we are only talking about numbers which are complete. Even if they are having negative sign with them, still the number is complete. But suppose if we are talking about the part of something or fraction of something, and also the in case of negative numbers also, then how to represent those numbers? Then no, those numbers can be represented using rational numbers. So what are rational numbers then? Rational numbers are those numbers which are having a particular form that is known as P by Q form. So in this form, when a number is written in this form, or you can call it a fractional form also, then there's one more condition, that Q cannot be equals to 0. Then what are P and Q? P and Q can be any integer number, but the number should be written in this form: a number on top and the number in bottom. the number on top is known as the numerator part of the number, and the number in bottom is known as the denominator part. But p and q both can have any value of integers, but q can never be equals to 0. This is the primary condition. Now, when numbers are written in this form, they are known as rational number. But when we cannot write the numbers in this form, then we can call such numbers as what? Irrational numbers. So irrational numbers are those numbers which cannot be written in the form of p by q, where p and q are integers and q is not equals to 0. So this is the basic overview of different type of numbers. You are already familiar with natural whole integers. Also rational numbers, with rational numbers you are also familiar. This is the basic definition, basic idea behind rational numbers. Then we are having irrational numbers which cannot be written in the form of p by q. We are going to discuss about them in detail in this session only. Okay. So first, rational number. Before understanding the concept of irrational numbers, we should be knowing what are rational numbers. So rational numbers, as I told you, can be written in the form of p by q. P and q can be any integer number, but q cannot be equals to 0. They are having a certain decimal expansion of their. What type of decimal expansion can there be of rational numbers? It can be terminating type like 2.5, 3.40, 9.87654. But if we are terminating the decimal at any point, then we are gonna call that as decimal expansion of terminating type, and that expansion will be always of rational numbers. So if you try to convert that decimal number into any certain type, you can convert it back into any rational number. Then one more type of numbers decimal expansion can be called as a rational number, that is repeating type, where the decimal keeps on repeating itself. As you may have seen in your previous classes, that we can use bar over the numbers to represent the repetition, correct? Example, like 1 by 4. If I divide 1 by 4, then the answer that I'm gonna get is 0.25, a terminating type of decimal expansion, right? So this type of numbers are nothing but the rational numbers, or you can call it that the rational number will always have either terminating type or recurring type of decimal expansion, where a certain value keeps on repeating itself. Like in this example, when we are dividing 7 by 9, we are gonna get the answer as 0.777777 and so on till infinity. So there is no stopping point here. But we can see that in the repetition, only one value is keep on repeating itself. So we can represent this using bar. So how to write this value? It can be written as 0.7 and bar over 7. So it means that 7 will keep on repeating itself. I can give you one more example, a basic one. If I am dividing 1 by 3, the answer we are going to get is 0.333 and so on till infinity. So I can convert this number back to 0.3 and bar over 3. So bar is representing that 3 keeps on repeating itself. So this type of decimal expansions are also of rational number only. If you are having, if in exam, the examiner is asking what type of decimal expansion a rational number can have, then you can write that there will be of two types, either terminating or non-terminating repeating. Then irrational numbers. The number which are not rational are irrational. Simple. But definition wise, you can write it like this. The numbers which cannot be written as a p by q in this form, p by q, where p and q are integers and q is not equals to 0, then those numbers are known as irrational numbers. Now someone is asking why we are considering this condition in case of rational numbers, that q should not be equals to 0. Okay, let me explain this part. Why we are not keeping q as 0? We can put value of p as 0, that is fine, but we cannot put value of q as 0. So understand this in this way. We know what are fractions, correct? Fractions are a number on top, a number in bottom, correct? There are three type of fractions: proper, improper, mixed one. Suppose if we are having a proper fraction, So the numerator must be lesser than denominator. Suppose if I am going with 2 by 5. What is the meaning of 2 by 5? What is the meaning behind this number, this fraction or this rational number? It means that we are considering 2 parts out of total 5 parts. So number in denominator is representing that how many parts we are considering. The number in denominator is representing out of how many parts. Same if I am going with 3 by 7, then we are considering 3 parts out of total 7 parts. Now suppose if we are putting 0 in the denominator with any number on top, suppose 5 by 0, then can we consider 5 parts out of total 0 parts? No, we cannot. As of now, we cannot define this situation. That's why any number when divided by 0 is still not defined. So that's why we cannot put the value of q equals to 0. That is the only reason. Now I did explain using fractions, no? The difference between, the main part why we are not putting q equals to 0 using fraction. Then what is the difference between rational number and fraction? There is only one basic difference, that fraction is just the part of a whole, correct? It means part of a whole number. So fraction can never be a negative value, but rational numbers can be negative also. Now, irrational number. The definition I told you that the number cannot be written in the form of p by q, where p and q are integers and q is not equals to 0, correct? Decimal expansion type of irrational number. In case of rational number, it was terminating and terminating and repeating type. Here we have non-terminating, non-repeating type of decimal expansion. It will not terminate, it will not repeat itself. So this type of decimal expansion is of only one type of numbers, that are irrational numbers. Examples would be square roots of non-perfect squares. So we are having different numbers, either it can be a perfect square or it cannot be a perfect square, correct? So what perfect squares we know, 4, 9, 16 and so on, correct? Non-perfect squares are every number in between, like root 2, root 3, root 5, root 7. They don't have perfect square value. So all of them are what? Irrational numbers, because they must be having non-terminating, non-repeating type of decimal expansion. Then we have pi. Now pi is very interesting, because usually we are using the value of pi as what? 22 by 7, correct? Aren't we using this value? We have been using this value from a very long time. But let me ask you one thing, that here in the value of pi, isn't it a p by q form? It is. 22 is the p, 7 is the q. Also, both the numbers 22 and 7, or p and q in this case, are integers. 22 is an integer, 7 is also an integer. Also, the value of q is not equals to 0. So shouldn't we be calling pi a rational number? But I am saying that pi is irrational number. What is the reason behind this? Actually, the 22 by 7 is not the actual value of pi. We are only using this value just for the simplification of calculation. We are only keeping our calculation simplified. That's why we are using this value 22 by 7. The actual value of pi is a number which is having a decimal expansion of type non-terminating, non-repeating. So that's why pi is an irrational number. So this is the decimal expansion of pi, 3.1419265358 You can see now there is no certain pattern. Then you can call it repeating type of decimal expansion, and it is not terminating. You can still find the numbers after this value also. So that's why pi is the most famous irrational number, one of the most famous irrational number. Then we have Euler's number, E, value of E. So the value of E is also having decimal expansion of type non-terminating, non-repeating. 2.718281828459 and so on. There is no certain pattern that you can call that it is repeating itself, correct? Then the golden ratio. Golden ratio is having value as 1.6180339887 and so on. So this number is also having non-terminating, non-repeating type of decimal expansion. So that's why all these numbers are prime examples of irrational numbers. Understood? Now we understood the basic concept of rational number, irrational number. Why we are studying about them here in this chapter? The name of the chapter is real numbers. So what are real numbers then? We haven't talked about real numbers till now. Or we did? Yes, we did talked about real numbers. All the numbers that are rational plus all the numbers that are irrational together make real numbers. Real numbers are those numbers which we can plot on the real number line. You have been plotting numbers on the real number line, right? Also, you have seen how to plot root 2 on real number line in 9th class, correct? So it means any number that can be represented on the real number line is real number. So all the rational numbers and all the irrational numbers can be represented on the real number line. Now, just to make you understand what is happening here, we have natural numbers 1, 2, 3, 4, 5, 6 and so on till infinity. Then we have whole numbers 0, 1, 2, 3, 4 and so on till infinity. So it means natural numbers are nothing but a part of whole numbers or a set of whole numbers, correct? Subset of whole numbers. Then integers are what? All the whole numbers plus the negative counterpart of the positive numbers. So it means all the whole numbers are subset of integers. Then we are talking about rational numbers. So all the integers are subset of rational numbers. Now here the main problem is that if I am having a number 3, then is it a rational number or is it not? Or minus 5, are they rational numbers? They are integers, I am aware of this, but are they rational numbers also? Yes, they are. But I cannot see the p by q form. Any number that is written in this form can also be written like this, divided by 1. This will not change the value of the original number, and also using this form I can see that the number is now in the p by q form. 3 by 1 p by q. Both the numbers are integers? Yes, they are. Is q equals to 0? No, it is not. So it means both the numbers are rational numbers also. So that's why integers are subset of rational numbers. Then we have irrational numbers, a different set where we have different numbers. So both of them together make real numbers, as I told you. So the set of real numbers is all numbers that can be written on the number line, that can be represented on the real number line. It consists of the set of rational numbers and the set of irrational numbers. So that's how real numbers came into the picture, because both the sets can be represented on the real number line easily. Now let's move on to other things that are very important with if you look at them from the exam point of view. You understood the concept of real numbers, correct? Rational, irrational and everything. Now let's move on to some other things that you can expect in this chapter. Things would be LCM, HCF or this formula. LCM, you know the concept. What is LCM? Least common multiple, correct? So here actually it is least common multiple. Then HCF, highest common factor, correct? So we know how to find these values, correct? The LCM of 2 or more than 2 numbers, HCF of more than 2 or more than 2 numbers. We know the concept. We know how to find it. Now, suppose 2 numbers are given to you. Any 2 numbers, A and B suppose. Then the LCM of A and B when multiplied with the HCF of A and B is gonna give you result as the product of those 2 numbers, or basically A into B. So this is one very useful formula. Suppose in your exam 3 values are given, LCM, HCM and one of the number. Can you find the second number? Easily we can find, because we know this formula, correct? So this is very useful. Just remember this. Now let's talk about different things that we are going to use in this session. First thing is coprime. You are already familiar with this concept. I'm going to tell you quickly what are coprimes. Prime numbers we understood, na? Prime numbers we know. What are prime numbers? Those numbers which are having only two factors, 1 and the number itself. Other than these two, there is no factor of those numbers, correct? Examples would be 2, 3, 5, 7, 9, 2, 3, 5, 7, 11, 13 and so on, correct? All these numbers are prime numbers. Then what are co-primes? What are co-primes? Co-prime numbers are not necessarily the prime numbers. It can be any two number, even if they are composite numbers, but they don't share any common factor among them, such as 8 and 9. So 8 and 9 both are composite numbers, aren't they? Yes. Do they have any common factor among them? No, because the factors of 8 are what? 1, 2, 4 and 8 itself. What are the factors of 9? 1, 3 and 9 itself. Is there any common factor other than 1? No, there is not. So they are not sharing any common factor other than 1. So they are known as co-primes to themselves. Even if they are composite numbers, but they can be co-primes. They cannot be prime, but they can be co-primes. So the definition is written like this only. These are two or more integers that share only one common factor, that is 1. Because 1 is the factor of every number, meaning that their highest common factor is 1. It means if two numbers are having HCF equals to 1, then they are co-primes. Then rational numbers are not by co-primes. Means that rational numbers are not necessarily co-primes to each other. They can be, they cannot be. But when we write them in lowest terms, the numerator and denominator becomes co-prime. Suppose if we are having a rational number 20 by 30. It is a rational number, p by q form. Both the numbers are what? Integers, and also q is not equals to 0. But this is not the lowest form or not the simplified form, correct? It can be any equivalent rational number to any other rational number. Right now, they do have some common factors among them. And what is that? It is the highest common factor among them is 10, correct? If I divide both the values by 10, then I'm gonna left with 2 by 3. Now this is the lowest form. Whenever we are writing any rational number in its lowest form, then we can see that the numerator and denominator will always be co-primes to each other. That is one thing that you need to remember. Understood? We are gonna apply this concept of co-primes in one of the theorems. So please do remember this. Very easy. That two numbers, if they are not having any common factor other than 1, are co-primes to each other. Now let's talk about different type of numbers so that we can understand the fundamental theorem of arithmetic. This is the concept that you can expect a problem from in the exams. Now, composite numbers are those numbers which are having more than two factors. Simple as that. If a number is having more than two factors, 1 and the number itself, then that number is composite number. Composite numbers can be expressed or factorized as product of primes. If they are having more than two factors, then we can write them in their prime factorization form, or we can factorize them, or we can write the number as product of its primes. Now, and this factorization will always be unique apart from the order in which the prime factor occurs. For every composite number, the prime factorization will always be unique. What is the uniqueness? I will explain this uniqueness part using one example. But before that, composite number, I told you the number that are greater than 1 but are having more than two factors, correct? Prime numbers, they will always be having only two factors, 1 and the number itself. Prime numbers are exactly two factors, such as 2, 3, 5, 7, 11, 13, 19 and so on. Then uniqueness, what is the uniqueness? Suppose if I am considering any composite number, suppose if I am going with 10, very basic number. What is the prime factorization of 10? Prime factorization means, okay, let's start the session. So hello everyone, welcome. I am Sambhav, your senior math instructor. Today we are going to talk about numbers. Not only numbers, but real numbers, the first chapter in your class. So I will wait for 2-3 minutes so that everyone method that you have used previously in your classes. So I'm gonna write 360 like this. Then the smallest prime number that I can think of which can divide 360 is 2. So I will go with 2. So what are we left with? 180. Again it is divisible by 2. 90. Again by 2. 45. This time it is not divisible by 2 because this is not even number. Now with which prime number, the lowest prime number that can divide this 45? 3, because sum of the digit is 9, so 9 is divisible by 3, so 45 is also divisible by 3. 15. Again 15 is also divisible by 3. 5, and 5 is only divisible by 5. 1. So these numbers that you are seeing here are nothing but the prime factors of 360. So how to write this? You are gonna write 360 and equals to sign. Then you will write all the values keeping multiplication sign in between. So 2 into 2 first, then 2 again, into 3, into 3, into 5. So this is the prime factorization of 360. 360 will always be having this prime factorization irrespective of the order in which the prime factors are written. Correct? These numbers, when they are multiplied in this way, having this much power, is gonna give you 360 only. Now these can be written in the exponential form also. So how many times 2 is being multiplied with itself? 3 times. So it can be written as 2 raised to the power 3. How many times 3 is being multiplied with itself? Twice. So 3 raised to the power 2. And 5 once only. So 5 raised to the power 1. This is also one of the form to write the prime factorization of any number, the exponential form. Then now let's find the prime factorization of one more number, 540. Same way we are going to find the prime factorization, the ladder method. 540. So the smallest prime number that can divide 540 is 2. 270, again divisible by 2. Then 135, not divisible by 2, but we can go with 3. Then 45, 3 again, 15, 3 again, 5, and 5, 1. So these numbers that we are getting here on the left side of the ladder method are nothing but the prime factors of 540. Correct? So we are gonna write it in this way. 540 can be written as 2 into 2 into 3 into 3 again into 3 again and then into 5. Again, I'm gonna write the value in factorized form. Sorry, exponential form. Yeah. So that would be 2 raised to the power 2 because 2 is being multiplied with itself twice. 3 raised to the power 3 into 5 raised to the power 1. Now you understood how to find the prime factorization of any number. Easy. What is the benefit? First, that we can find the HCF of any two number easily, two or more than two numbers. Using prime factorization, you can easily find the HCF of two or more than two numbers very easily. How? First thing first, you are gonna write the prime factorization of 72. So let's find the prime factorization of 72. 72. So 2, 36, 2, 18, 2, 9, 3, 3, 3, 1. So 72 prime factorization is 2 into 2 into 2, or 2 raised to the power 3 into 3 into 3, that is 3 square. What is the prime factorization of 120? Let me erase this. Then we are gonna find the prime factorization of 120. If you are quick enough, you can find it before me. So let's see who's gonna do it first. 60, then 2, 30, 2, 15, 3, 5, 5, 1. So the prime factorization is 120 is equals to 2 into 2 into 2 thrice. So 2 cube into 3 once. So 3 raised to the power 1 into 5 raised to the power 1. Now, after finding the prime factorization, what should be done? How to use this prime factorization to find the HCF of these two numbers? So, HCF is highest common factor, correct? That factor which is highest among any two numbers. How to find that value which is the highest factor? So, all the factors of 72 are 2 into 2 into 2 into 3 into 3, correct? For 120 it is 2 into 2 into 2 into 3 into 5. So these are all the, if I can find the common ones, the common factors among these two numbers, that will be nothing but the highest common factor between these two numbers, correct? So we are gonna do that only. We are gonna find lowest power of each common prime number in the prime factorization of the given numbers. Lowest power. So first we need to realize which prime numbers are common between these two. The easy way I will tell you. So 2 is present in 72, 2 is also present in 120. First I am gonna write the number only, the prime number without power. I will tell you how to identify the power. Then is there any other number that is common? 3. 3 is also here, 3 is also here. 5 is common kya? No, it is not, because 5 is present in case of 120 but not in the case of 72. So we are not gonna write 5 here. Then how to select the power? See, the lowest power it is written. Here the power of 2 is 3, power of 2 is 3 here also. So both are having same power, so we can directly go with 3. So 2 will be having 2 raised to the power 3. What about 3? Here the power of 3 is 2. But here the power of 3 is 1. What is the lowest power? 3 raised to the power 1. Correct? So we are going with 3 raised to the power 1. No. Now we need to multiply them or expand them. 2 cube is 8. 8 into 3 is what? 24. So this is the HCF of these two numbers, 72 and 120. That is 24. So this is how you can use prime factorization to find the HCF of any two or more than two numbers. Easy. You are gonna write the prime factorization first, then you are gonna look for the lowest power of each common prime factors. Correct? Then you are gonna multiply that. That will be your HCF. Easy, no? Very easy method. Now, here I have given a word problem related to HCF somehow, but you need to analyze the problem first. Let's look at the statement that is written here. A school wants to arrange students of class 10th and 9th for a drill. Okay, they are arranging two classes. Then there are 96 students in class 10th and 144 students in class 9. So there are too many students. So of course if they are arranging them for a drill, then they must be arranging them in particular number, no? Find the maximum number of students in each row. So it means they are creating rows now. So in each row, there must be having equal number of students. So we need to find the number of rows and each row must be having equal number of students. Okay. And that would be the highest value. So it means we need to find the maximum number or HCF of these two numbers. Second part is how many rows we can find in this way. If we are having the highest common factor, we can easily find the number of rows. So first, let's find the HCF. So first part, HCF. How to find HCF? I'm going with prime factorization. So prime factorization, I need to find of two numbers, 96 and 144. So what is the prime factorization of 96? I will directly write, 96 would be 2, then 48 into 2, 24 into 2, 12 into 2, 6, 2 into 3. I will recheck again. 3 into 2, 6 into 2, 12 for 24, 48, 96. Okay. If I need to write this, I can write it in this way. 2 raised to the power of 5 into 3 raised to the power 1. Then we are having 144. So I can go with 2, 72, 2, 36, 2, 18, 2, 9 into 3 into 3. Correct? 3 into 3, 9 into 2, 18 into 2, 36 into 2, 72 into 2, 144. So this is the prime factorization of 144. So 1, 2, 3, 4. 4, 2. So 2 raised to the power 4 into 3 into 3, 3 square. If you are not comfortable in writing the prime factorization like this, you can always choose ladder method. Okay, that is easier. Now, how to find the HCF? We know the concept that HCF will always be the lowest power of each common prime factor. Correct? How many factors are common here? 2 and 3, both are common. So I will write 2 into 3. What is the lowest power of 2 in between these two? 2 raised to the power 5, 2 raised to the power 4. So 2 raised to the power 4 is lower. Then what is the lowest power in between these two? 3 raised to the power and 3 raised to the power 2, 3 raised to the power 1. 2 raised to the power 4, 16. 16 into 3, 48. So the HCF of these two numbers, 96 and 144, is 48. So it means they can create rows having 48 number of students, the maximum 48 number of students they can get in one row. So how many rows they can create now? That is second part, no? Now, let me erase everything. We know that the HCF is 48. It means the maximum number of students in each row can be 48. Now, for 10th class, how many students are there? 96. So number of rows would be 96 divided by 48. 96 divided by 48 is equals to 2 rows. Then rows of 9th class, number of rows, 144 by 48, 3 rows. So how many total number of rows? 2 plus 3, 5. So the total number of rows is 5. This is your answer. Total, they can make 5 rows. So this is how you can apply the concept of HCF and how to find HCF using prime factorization. Easy? Now, fifth example. HCF and LCM of two numbers are given. the same concept that I told you, that if the HCF and LCM of any two numbers are given, and if one of the number is given, then you can easily find the second one, because the formula that you can apply here is LCM into HCF is equals to product of the two numbers. So LCM and HCF is given as 18 and 180. So HCF is 18, LCM is 180 respectively. If one number is 36, find the other number and verify the result using prime factorization. We need to verify also. Now, HCF is, sorry, the formula that we can use is HCF into LCM is equals to product of two numbers. HCF we know 18. So it means 18 into 180 is equals to, one number is 36. The second number I am considering as X as of now. So X can be found using, if I just transpose this 36 to left side, so it is gonna give us 18 into 180 by 36 is equals to X. This is 2, oh sorry, this is 2 and this is 90. Therefore, X is 90. It means this second number is 90. Now, how to verify this? First, let me erase everything. So, one number is given as 36. So, what is the prime factorization of 36? That is 2, 18, 2, 9, 3 into 3. Correct? Also, 2 square into 3 square. Then, what is the prime factorization of 90? That would be 2, 45, 3, 15, 3, 5 into 5. So it would be 2, 1 into 3 square into 5 raised to the power. So HCF is the lowest power of each common prime factor. So HCF of these two numbers would be, the common prime factors are 2 and 3, correct? So it would be 2 into 3. The lowest power of 2 is 1. Lowest power of 3 is 2. So it would be 2 into 3 into 3, that is 18. Correct? That is the HCF. LCM. LCM is the least common multiple. So the value of LCM can be found using this method. The highest power of each prime factor. So how many prime factors? You can see different prime factors, 2, 3 and 5. What is the highest power of 2? Here, 2 square. Highest power of 3 square. Highest power of 5, 1. 2 square 4 into 3 square 9. 4 into 9, 36. And 36 into 5, 180. So it means that this number is correct. That second number is 90, and we are even verifying this using prime factorization. Correct? So now we are done with the different type of problems that you can expect in this topic, the fundamental theorem of arithmetic. So for now, we are gonna take 5-minute break. I'm gonna meet you again in 5 minutes. You just get it done with your things. If you want to drink water or anything, I will come back in 5 minutes. Okay? Now I hope you all are back. Now let's continue our discussion on this chapter, real numbers. So till now we understood the basic concepts of this chapter, and then we saw the fundamental theorem of arithmetic, what are the uses and how to find HCF and everything, correct? Now let's move on to different segment of this chapter, that is irrational numbers. So in your previous classes, you may have get the idea behind rational numbers, correct? Also earlier in this session, I told you what are irrational numbers. The numbers which are real numbers but are not rational numbers are irrational numbers. The basic idea is this only. But the correct definition would be, if we cannot express any number in the form of p by q, where p and q are integers and q is not equals to 0, then those numbers are known as irrational numbers. Okay. Now q is not equals to 0 and everything I did told you na. Now decimal expansion is of two types, non-terminating and non-repeating. Only one type, sorry. This is having one type of decimal expansion which is not gonna repeat itself and not gonna terminate. That would be the decimal expansion of these type of numbers that are known as irrational numbers. Examples would be pi, e, or root 2, root 3, root 5, the square root of any non-perfect squares. So now in this particular session, we are going to prove the irrationality of any number. How to prove the irrationality? Till now in 9th class, you may have been seen what are irrational numbers, how to plot them on the number line also, correct? But here I am going to show you how to prove the irrationality of any irrational number. Before that, we need to understand this theorem. This is the main part of the proof of irrationality of irrational numbers. What is this theorem? This theorem is about the prime numbers. Suppose if we are having any composite number, then that composite number must be having a particular prime factorization, correct? As I told you in that slide, that prime factorization of every composite number will always be unique to that number itself, correct? That is the uniqueness of prime factorization, correct? Suppose if we are having any prime number, any composite number, let me give you a brief overview before explaining this concept. Suppose if we are having 12, what is the prime factorization of 12? 2 into 2 into 3. This is the prime factorization, correct? Now, as you can see, that 2 has been repeated twice, 3 once. Now, even if I multiply just by changing the order, I will always get 12 only. Suppose if I am finding 12 square. So what is square of any number? We are multiplying the number with itself, correct? So it means 12 square is 12 into 12. If I am writing this 12 in its prime factorization form, then this will become, in bracket I am writing this 2 into 2 into 3. Same I am doing for this 12 also, so 2 into 2 into 3. Now let me ask you one thing. If I am saying that any number that is present here, if I am considering only one value, suppose if I am considering 2, sorry. So these numbers are nothing but the factors of 12 square, correct? So if I am saying that if 2 is a factor of 12 square, then 2 is also a factor of 12. If I am only choosing 2 once, then basically every factor here is written twice as many times that it is present in the prime factorization of the number itself, correct? So in the square value, it will always be in the double amount. So the main idea behind this theorem is, any prime factor which is present there in the prime factorization of square of any number will always be there in the prime factorization of the number itself without having the square value. This is the basic idea. So here we need to prove this first. So let me erase everything first. Statement would be, let P be a prime number. P can be any prime number. If P divides A square, look at this. if P divides A square, it means P is present in the prime factorization of A square, correct? Then P divides A as well. It means P is gonna divide the non-square value or the square root value of A square as well. Of course, it is gonna divide, because as I have shown you that square value will always be having twice as many prime factors, same prime factors, as it is having in the non-squared value, correct? So where A is any positive integer, this is the basic theorem. This theorem we need to understand, because we are going to use this theorem in the proof of that irrationality of any number. Proof of this theorem is, let the prime factorization of A be as follows. So A is the main number, correct? Normal value is A. So the prime factorization of A, we are understanding this one as P1 into P2 into P3 and so on till Pn. Suppose we don't know the exact numbers, but these are the prime numbers. P1, P2, P3 and so on till Pn can be distinct, or they not necessarily need to be distinct. They can be same also. Now the same is written here, where P1, P2 and so on till Pn are primes. These are different prime numbers. Oh sorry, these are prime numbers, not necessarily distinct. They can be same, they can be different. Therefore A square, what is A square then? A square is nothing but A into A, correct? So then I am opening the first A, I am writing the first A as product of its primes. So it will become P1 into P2 and so on till Pn. Second A also P1 into P2 into so on till Pn. Now P1 is being multiplied with itself twice. So it will become P1 square. Same goes for P2, P2 square. Same goes for Pn, Pn square. So prime factorization of A square will be P1 square into P2 square and so on till Pn square. Every prime factor is being multiplied with itself twice, so it will become squared value. Now according to the statement of the theorem, it is given to us that P divides A square. If P is a prime number and it is dividing A square, then it basically means P is one of the value from P1, P2, P3 and so on till Pn, correct? It must be from those only because of the uniqueness, correct? So if given is that P divides A square, then therefore from the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square because of the uniqueness part only. I told you na, if you are finding the prime factorization of particular number, that will always be unique, or same goes from the other side. If you are multiplying a particular set of prime numbers, then you will always get a unique number, correct? If given is that P divides A square and P is already prime number, so it must belong to these values P1, P2, P3 and so on till Pn, correct? Now, however, using the uniqueness part of the fundamental theorem of arithmetic, we realize this thing, P is one of P1, P2, P3 and so on. Since all these numbers P1, P2, P3 and so on till Pn are also prime factors of A, then it means P divides A as well, because P is one of them. It can be any value. So it means P divides A as well. So this is the main theorem that we are going to apply in case of proof of irrationality of any number. How? Using this, we are going to contradict our statement. We cannot directly prove the irrationality of any number. There we will be using the proof by contradiction. What is proof by contradiction? Suppose if I am saying that a particular number is an irrational number and I need to prove it. So first I'm going to consider that it is not an irrational number, it is a rational number. Then later on in my proof of that I will be proving it as irrational number, I will get stuck somewhere. I will be contradicting my initial statements. Why the contradiction will arise? Because of our wrong assumption. So that is enough to conclude that the number is irrational. So this is known as the proof by contradiction. You are gonna assume one thing first, then you are gonna contradict yourself, then you are gonna say that no, this is not true, the opposite of this is true. Okay. First, the basic number that we need to prove as irrational is root 2. This is the easiest one and you are gonna understand the idea behind the proof. Okay. So we need to prove that root 2 is irrational. If we need to prove that root 2 is irrational, so I will go by proof by contradiction. So I will consider that root 2 is not irrational, it is rational. Okay. Then in the later part of the proof, I will contradict myself. Okay. Now, let us assume to the contrary that root 2 is rational. If any number is rational, then it can be represented in the form of p by q. We cannot represent irrational number as p by q, but if any number is rational, then we can represent it using p by q form, correct? Where p and q are integers and q is not equals to 0. So here we are considering root to be a rational number. So there must be a p by q form. So here we are considering two integers a and b, where b is not equals to 0, such that root 2 is equals to a by b. So a and b are two integers, correct? This is our p by q form. Now we can do one thing. We can consider a and b to be co-primes. Why we are considering them to be co-primes? Because previously I explained you one thing, that rational number when written in the most simplified form, their lowest form, will always be having co-prime numbers in numerator and denominator. This is very much necessary. You need to write it in this way only. A and B are co-primes. If A and B are co-primes, even if they are composite numbers, even if A and B can be composite numbers, but still they will not be having any common factors among them. Correct? Now, if I am writing root 2 is equals to a by b, now the main problem here is this under root sign, correct? So first I need to get rid of this. I will do one thing, I will square both the sides. So it will become under root 2 whole square equals to a by b whole square. Root and square are gonna cancel each other. So it will become 2 is equals to a square by b square, correct? Now we are gonna transpose this b square to left side. So the equation will become 2b square is equals to a square. Now let me ask you one thing. A and B are co-primes. They are not having any common factors among them. But here we are seeing a number 2 in such a way when it is being multiplied with b square is giving me a square. It means that a square is divisible by 2. Correct? A square is divisible by 2. That is for sure. Otherwise, we must not be having this equation. 2 is a prime number also. It means that if I do the prime factorization of a square, 2 will be present there. Correct? Now, remember the previous theorem, theorem number 1.2. That is, if there is any number p, prime number, and if p divides a square, then p divides a as well. Correct? So here 2 is prime number, 2 divides a square, so it means 2 divides a as well. Correct? So using this theorem, we are concluding that 2 divides a. So if 2 divides a, so there must be any number that when multiplied with 2 is gonna give us a. Correct? Suppose that number is c, that is integer c. So here we can rewrite this situation as a is equals to 2 into c. C can be any integer. Huh? Now square this equation both sides. So it will become a square equals to 4 into c square. Now a square is also equals to 2 into b square. So we are going to substitute this value here. So 2 into b square is equals to 4 into c square. 4 and 2 are divisible. So b square value is coming as 2 into c square. So when 2 is being multiplied with c square, then it is giving us the value of b square. Again, look at this equation. 2 is what? 2 is a prime number, correct? And 2 is being multiplied with c square. Forgot about c square, whatever the value of c square is. But 2 is a prime number and it is present in the prime factorization of b square. Whenever we are writing the prime factorization of b square, it must be having 1, 2. So it means that 2 divides b square. If 2 divides b square, then it means that 2 divides b as well. So we can see one thing, 2 is dividing a, 2 is dividing b as well. But remember, initially we assumed that a and b are co-primes, that there is no common factor other than 1 between them. But here we can see that at least one more common factor is there, that is 2. Other than 1, there is one more common factor 2. But how can this be possible? If we are considering a and b to be co-primes, how can we come to this situation that we can see now that it is having one more common factor? So this contradicts the fact that a and b are having no common factors other than 1, or it means that they are co-primes. This contradiction has arisen because of our incorrect assumption that root 2 is rational. This contradiction has only arisen because of our wrong assumption of root 2 as rational. So it means root 2 is irrational. This is proof by contradiction. Because of this major contradiction, we can directly say that root 2 is not rational, it is irrational. This is the proof. You can prove any number, be it root 2, be it root 3, root 5, root 7, any number using this method. First, consider them to be rational, find the square, then you can see that that number is a prime number and is also a prime factor of a square. If it is a prime factor of a square, it is also a prime factor of a as well. Later on, you will realize that same number is a prime factor of b also. But initially, you are considering a and b to be co-primes. That is contradicting our initial statement. So this contradiction has arisen because of our wrong assumption that that particular number is irrational. So from here, we can conclude that this number is irrational. Initially, we assume that it is rational, but that is wrong. So it means that number is irrational. You can prove any number to be irrational, which are irrational of course, using this method. Okay. Now, different type of problems that you can expect in your exam. One type is this, that you need to prove root 2, root 3 as irrational. Correct? The other type would be this type of problem. We need to prove that 1 by root 5 is, we need to show is rational or irrational. So first we are going to consider that let 1 by root 5 is rational number. If it is a rational number, then it must be having p by q form. So we are going to consider two integers a and b. A and b are two integers such that they are co-primes and b is not equals to 0. This you need to follow every time. Now, I can write, let me rewrite this. I don't know what I have written here. Now, 1 by root 5 can be written in this form now, correct? Now, look at this. 1 by root 5 is equals to a by b, because 1 by root 5 is a rational number. We can do one thing. We can transpose the numbers or we can take the reciprocal on both sides. So it will give us root 5 is equals to b by a. Now, we know that in your exam paper, you can directly write, we know that root 5 is an irrational number. We need to prove 1 by root 5 is whether rational or irrational. So from here, we are considering it to be a rational number. But here, after taking the reciprocal, we can see that root 5 is equals to b by a, which is a p by q form where both the numbers are integer and q is not equals to 0. This is not possible because an irrational number can never be written in this form. And we know for a fact that root 5 is an irrational number. This is not possible. This contradiction has arisen because of our wrong assumption that 1 by root 5 is a rational number. So from here we can conclude that 1 by root 5 is an irrational number. Directly you can write this. You will get full marks. One more type of problem, correct? Now let's see one more. Root 2 plus 7. We need to show whether it is rational or irrational, right? Now, we know that root 2 is irrational. We just saw the proof. But this time we are adding one rational number with irrational number. Let me give you a fair idea about this. This is basically irrational. Whenever you are adding, multiplying, dividing any rational number with irrational number, the whole value will become irrational itself. Now, how to prove this? Let root 2 plus 7 to be a rational number. If it is a rational number, then it must be having p by q form. Again, we are gonna go with a and b are integers such that a and b are co-primes and b is not equals to 0. So it means root 2 plus 7 is equals to a by b. Now, we know for a fact that we know a major property of rational numbers, that rational numbers are closed under addition, subtraction, division except 0 and multiplication. Rational numbers are closed under every operation. One condition is there, that division except 0. So it means that whatever operation we are performing in between two rational numbers, we are gonna end up with rational number only, correct? This we know. So if I transpose this 7 to right side, the equation will become root 2 is equals to a by b minus 7, correct? The equation will become something like this. This is closed under the any operation. Here the operation is minus, the subtraction. Both values are rational numbers, a by b and 7. Rational number when subtracted by rational number is gonna give us rational number itself. This is a rational number. Is root 2 a rational number? No, it is not. So this is contradicting our statement. Which statement? That root 2 plus 7 is a rational number. So it means that this is not true, because rational number cannot be equals to irrational number. This contradiction has arisen because of our wrong assumption that root 2 plus 7 is rational number. So from here we can directly conclude that root 2 plus 7 is not rational number. Understood? There's one more way to understand this. We know, I'm just giving you the idea. This is not the actual proof. You don't need to write this method in your exam. But look at this, just to make you understand. Root 2 is having decimal expansion of type non-terminating, non-recurring, correct? So it is basically 1.414 and so on, correct? So if I'm writing or if I'm adding 7 with this decimal expansion, so what will it become? Suppose if I'm adding 7 here, so it will become 8.414 and so on till infinity, non-terminating, non-recurring. Now look at this new number. It is having the same decimal expansion as it is having, because we are not adding anything after decimal. Even if we are adding, we must not be getting any particular pattern, correct? So the decimal expansion is not changing. It means the resultant number is also an irrational. This is just for the idea why, what is happening here. But the proof that you need to write in your exam is the previous one, okay? Prove that 6 minus 4 under root 5 is an irrational number. given that root 5 is an irrational number. The same method you need to apply here. We know that rational numbers are closed under addition, subtraction, division except 0 and multiplication. We are going to use this concept only. Let 6 minus 4 root 5 to be rational number. If it is a rational number, we are gonna consider two numbers a and b in such a way that a and b are co-primes, both are integers, and b is not equals to 0. So it means 6 minus 4 root 5 is equals to a by b. Transpose every value except 5. Already we know that root 5 is irrational, correct? So transpose every other value to right side. So minus 4 root 5 will become a minus b minus 6 plus 6 will become minus 6, correct? Minus 4 also I am going to transpose to right side. So root 5 will become minus a by 4b and plus 6 by 4. Again, we can rearrange the terms. There is no need, but I am going to rewrite this again. So root 5 is equals to this negative value to the right side, 6 by 4 will become 2 by 3, 3 by 2 minus a by 4b. Again, rational number when added, subtracted, multiplied or divide except 0 by another rational number is closed, correct? So it means rational number when multiplied, divided, except 0, added or subtracted by another rational number is gonna give us rational number only. So it means the resultant of all these values will give us rational number only. But so this is irrational number, this is rational number. They can never be equals to each other, correct? Because they are having two different sets. So this is contradicting our statement that 6 minus 4 root 5 is a rational number. So it means that this value 6 minus 4 root 5 is irrational number, correct? So this is how you can prove this. You need to remember this property that rational numbers are closed under addition, subtraction, division except 0 and multiplication. Whatever operation you are performing in between two rational number, you are always going to end up with rational number only. And here, whenever you are left with this situation where on one side only irrational number and on other side only rational number, then this is not possible. This is contradicting our statement. Then we can directly write that the given value is irrational number. So this is how you can prove such problems. Now, let's recap what we have understood in this session. Every composite number has a unique prime factorization, that is known as the uniqueness of fundamental theorem of arithmetic. Rational numbers can have two type of decimal expansions, either terminating or repeating type of decimal expansion. Then irrational numbers would be having only one type, non-terminating and non-repeating type of decimal expansion. Theorem 1.2 helps in understanding or in proving the irrationality of any number. This is very important, correct? So these are the topics that we covered in this session. I hope you gained something from this session and you understood every part of it. This is very easy chapter. You can easily score in this one. Although you can expect hardly 5 marks problems up till 5 marks from this chapter only. But 5 marks are 5 marks, no? Why lose them? So we are done with this session. If you are having any doubt, you can let us know in the comment section. We are gonna take your doubt and we are gonna solve them. So till then, bye bye from my side. We'll meet you in the next session.